1.1.5 The Substitution Model for Procedure Application. To evaluate a combination whose operator names a compound procedure, the interpreter follows much the same process as for combinations whose operators name primitive procedures, which we described in section 1.1.3. That is, the interpreter evaluates the elements of the combination and applies the procedure, which is the value of the operator and of the combination, to the arguments, which are the values of the operands of the combination. We can assume that the mechanism for applying primitive procedures to arguments is built into the interpreter. For compound procedures, the application process is as follows. To apply a compound procedure to arguments, evaluate the body of the procedure with each formal parameter replaced by the corresponding argument. To illustrate this process, let's evaluate the combination f of 5. Where f is the procedure defined in section 1.1 we begin by retrieving the body of f, the sum of squares of plus a of 1 times a of 2. Then we replace the formal parameter by the argument a by the argument of 5. So of course plus 5 and 1 times 5 and 2. Thus the problem reduces to the evaluation of a combination with two operands and an operator, sum of squares. Evaluating this combination involves three subproblems. We must evaluate the operator to get the procedure to be applied. We must evaluate the operands to get the arguments. Now, plus 5 and 1 produces 6, and multiply 5 and 2 produces 10, so we must apply the sum of squares procedure to 6 and 10. The values are substituted for the formal parameters x and y in the body of sum of squares, reducing the expression to plus square of 6 and square of 10. If we use this definition of square, this reduces to plus multiply 6 and 6, and so plus the product of 6 and 6 and the product of 10 and 10, which reduces by multiplication to adding 36 and 100 and finally to 136. The process we have just described is called the substitution model for procedure application. It can be taken as a model that determines the meaning of the procedure application insofar as the procedures in this chapter are concerned. However, there are 2 points that should be stressed. The purpose of the substitution is to help us think about procedure application, not to provide a description of how the interpreter actually works. Typical interpreters do not evaluate procedure applications by manipulating the text of a procedure to substitute values for the formal parameters. In practice, the substitution is accomplished by using a local environment for the formal parameters. We will discuss this more fully in chapters 3 and 4 when we examine the implementation of an interpreter in detail. Over the course of this book, we will present a sequence of increasingly elaborate models of how interpreters work, culminating with a complete implementation of an interpreter and compiler in Chapter 5. The substitution model is only the first of these models, a way to get started thinking formally about the evaluation process. In general, when modeling phenomena in science and engineering, we begin with simplified, incomplete models. As we examine things in greater detail, these simple models become inadequate and must be replaced by more refined models. The substitution model is no exception. In particular, when we address in Chapter 3 the use of procedures with mutable data, we will see that the substitution model breaks down and must be replaced by a more complicated model of procedure application. Applicative order versus normal order. According to the description of evaluation given in 1.1.3, the interpreter first evaluates the operator and operands, and then applies the resulting procedure to the resulting arguments. This is not the only way to perform evaluation. An alternative evaluation model would not evaluate the operands until their values were needed. Instead, it would first substitute operand expressions for parameters until it obtained an expression involving only primitive operators. Then it would perform the evaluation. If we use this method, the evaluation of f of 5 would proceed according to the sequence of expansions. Sum of squares plus 5, 1 times 5, 2. Sum of squares plus 5, 1 times 2. So plus 5, 1 plus 5, 1. Okay. Followed by the reduction. 6 times 6, 10 times 10, 36, 100. This gives the same answer as our previous evaluation model, but the process is different. In particular, the evaluations of plus 5 and 1 and multiply 5 and 2 are performed twice here, corresponding to the reduction of the expression multiply x and x. with x replaced respectively by plus 5 and 1 and multiply 5 and 2. This alternative fully expand then reduce evaluation method is known as normal order evaluation, in contrast to the evaluate the arguments, then apply method that the interpreter actually uses, which is called applicative order evaluation. It can be shown that for procedure applications that can be modeled using substitution, including all the procedures in the first 2 chapters of this book, that yield legitimate values, normal order and applicative order evaluation produce the same value. See exercise 1.5 for an instance of an illegitimate value, where normal order and applicative order evaluation do not give the same result. Lisp uses applicative order evaluation, partly because the additional efficiency obtained from avoiding multiple evaluations of expressions, such as those illustrated with plus 5 and 1 and multiply 5 and 2 above, and more significantly because normal order evaluation becomes much more complicated to deal with when we leave the realm of procedures that can be modeled by substitution. On the other hand, normal order evaluation can be an extremely valuable tool, and we will investigate some of its implications in chapters 3 and 4.